Okay, so in the last video, we talked about the nitrate molecule, NO3-, and I wrote the Lewis structure. It looks something like this. 1 double bond, 2 single bonds, and we figured out that the octet was satisfied for everything. We had 8 electrons around this oxygen, 8 electrons around this oxygen, 8 around this one, and 8 electrons around the central nitrogen. So therefore, it looks like a good Lewis structure. We also mentioned the square bracket notation because it is a charged molecule, so it's got a negative charge on it. Put the little negative sign out front, that's the correct notation. But a good question you can ask yourself is, why is the double bond in between this oxygen and this nitrogen? Why isn't it here? Why isn't it here? So the answer is there's no compelling reason to put it next to one or another. In fact, there's no difference between them. So this is the idea behind resonance structure. And what that means is we really could write this this way, just as valid, or we could also write this way. And the way we denote a resonance structure is with this double arrow pointing between the structures. Okay, that indicates that we have a resonance structure. And you notice this particular structure has 1, 2, 3 valid resonance structures. Okay, now here's a common misconception, and here's something I want to clarify to you. I don't want you to be confused by this. This sort of indicates that there's 1 double bond and 2 single bonds. That's not what a resonance structure is supposed to be conveying. And here's a common misconception that students have. It's one I had when I was a student, and I want to make sure you do not think this is true. So what this is not implying is that the bond rapidly flashes back and forth between this double bond here and here and here. Now, I don't really like the word resonance because it kind of, like thinking like a physicist, that sort of sounds like, you know, you hit the resonance frequency of something and something starts vibrating at exactly the right frequency. That is not what is happening, okay? NOT, 0, not nada. That is not happening, okay? Double bond is not rapidly flashing back and forth between these 3 things. What this is trying to convey is there's no correct way to really draw this Lewis structure, keeping the octet rules in mind. And really, it's some hybrid between these 3 things. In fact, there's 3 bonds and there's 1 double. It's about a 1 1/3 bond. So actually, the bond is a little different between a double bond and a single bond. Now, a later video is going to talk about the differences, but I'm going to introduce it right here. A single bond is longer than a double bond, is longer than a triple bond. So this is bond length. And a single bond is weaker than a double bond, is weaker than a triple bond. This is bond strength. Again, next video, we can talk more about this. There's a table with all kinds of numbers related to this, but take my word for it. If we were to measure the length of the bond, single bond is the longest of the bonds, longer than a double, longer than a triple. And the strength, how strong the bond is, single is weaker than a double, which is weaker than a triple bond. Triple bonds are quite a bit stronger than a single bond. So if this structure was correct, this would be implying that there are 2 longer and weaker bonds and 1 stronger bond. Correct? I mean, if this model was actually correct, what this would be saying is we've got a short, stronger bond and a longer, weaker bond. But in fact, when we do the measurements, that's not the case. There does not seem to be, there's not measurable any difference between these 3 bonds. They're all identical. It's not rapidly flashing back and forth. The electron's not rapidly moving back and forth between these and turning it into a double bond and a single bond. That is not happening. Here's what's actually happening. It is a hybrid of these three configurations, which we can't draw with a Lewis structure and still have the octets work out. So in other words, the Lewis structure is a model. It's a representation of what's happening, but it's not truly representing what's happening. It's actually some hybrid in between. Now, if you really want to draw a structure and represent the hybrid, it looks more like this. Nitrogen with kind of a partial bond that's a little bit stronger. Actually, I'm going to leave these lone pairs off because that's going to make it confusing. It looks more like this. It's more like a 1 1/3 bond. It's a single bond with a little bit more bond, and these are all the exact same bonds. All right, here's a way to maybe help you understand this. And this was explained to me when I was in college. I thought this was a weird illustration. Your book uses something with two dogs that are breeding, and they form a hybrid between the two dogs. I like that analogy because you all know what dogs are, and it helps you. The problem with the dog analogy is there really are such a thing as dogs. And the point I want to make to you again is this molecule does not exist. This molecule does not exist. This molecule does not exist. It's something in between these. So let me use another analogy that's sometimes used, which is admittedly a weirder analogy, but it maybe gets at what's happening a little bit better. So when explorers first went to Africa, they encountered a rhinoceros for the first time. They didn't exist in Europe, so no one had ever seen a rhinoceros. So when they came back from Europe, they said, there is this incredible creature down there. It's a big, huge creature. It's got a big tusk on its head. By the way, this is a picture I took in South Africa when I lived there, and no, rhinos do not walk across the street, generally speaking, when you're driving down the road. This is in a game park, so they do walk across the street in the game park. So here's some rhinos walking across the street. So they have this unique feature. They have this big horn, right, which you've seen before, of course, but they're huge, all right, big, fearsome animals with a big, huge horn. So people in Europe were saying, well, what the heck is this animal like? Now, obviously, no one had a iPhone and a nice digital camera they could take a picture and show them. They had to explain it to them. So they said, well, it's kind of like a unicorn. Unicorn has this big horn that's unique to it, 4 legs, and a griffin. Griffin is like an eagle and a lion's body. So it's like a big, huge creature with a horn on its head, kind of like a combination between a griffin and a unicorn. Now, why do I like this analogy? The reason why I like this analogy is there's no such thing as a griffin. It's a mythical beast. And sadly, kids, there's no such thing as a unicorn. Those are mythical beasts as well. But there is such a thing as a rhino. There's a real thing called a rhino, and you can kind of use this idea of two mythical beasts merged together to form this real creature. All right, that's where the analogy holds with mythical molecule that does not exist. This does not exist. This does not exist. But the real molecule is sort of a hybrid between these three things. It's a little bit shorter than a single bond and a little bit stronger than a single bond. It's like a 1 1/3 bond. That's the concept that we call resonance. And these are called resonance structures. When we can write a Lewis structure and write out another structure that has a valid Lewis structure, we call that a resonance structure. Okay, now let's introduce another topic. So we've just talked about resonance structures, and we've talked about how we can take a legit Lewis structure that might possibly be able to put a double or a triple bond somewhere else on the molecule, and we can write that as a resonance structure. Well, what happens if we can write two Lewis structures that both appear to be valid? And this gets us to an idea called formal charges. Now, this is another name I don't really like. I don't like the name of resonance structures because it sounds like the electrons rapidly flashing back and forth, or the molecules rapidly flashing back and forth between a couple different states. I already said in many ways that does not happen. Okay, there's no evidence that happens. So I don't like the name resonance structures because it kind of implies something that's not really happening. I don't really like the name formal charges because it sounds like there is a charge on an atom, which I'm going to tell you how to calculate in a second. But I don't like this name because there is no evidence there's a charge on these either. It's just a bookkeeping trick for figuring out good Lewis structures. So let's start with a molecule CS2. And perhaps you might want to stop the video right now and try to write the Lewis structure down for CS2. Most of you will come up with a specific Lewis structure. Some of you might come up with a different Lewis structure. But once you've written one, why don't you try to write another Lewis structure that appears to be equally valid? All right, so you can stop the video now, take a few minutes, see if you can write two different Lewis structures, neither of which violate the octet rule, and then we're going to see which one's the best one. Okay, if you're just coming back to me now, we're going to write the Lewis structures down. 4 times 1 is 4. Sulfur is 6 times 2 is 12. There are 16 total electrons. Central atom is carbon. Sulfurs are more electronegative. 2, 4, 6, 8, 10, 12, 14, 16. Count the octets. The sulfurs look good. The carbon does not look good. We're going to steal one of these lone pairs. We're going to steal another lone pair. And I need my little eraser here. I'm going to get rid of that guy. I'm going to get rid of that guy. And that's probably the Lewis structure that most of you came up with, CS2. Now, some of you might have come up with this structure. Now take a look at that structure. Let's count electrons. 2, 4, 6, 8, 10, 12, 14, 16. It's got 16 electrons. Octet rules, 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. Well, it looks like the octet rule looks good. There's no charges on this molecule, so that appears to be a decent Lewis structure as well. So notice what we've done now. We've created two different Lewis structures, neither of which violate the octet rule and account for all the electrons that we have available to us. So this is where this concept of formal charge comes in. We can actually use the idea of formal charge to help us figure out which of these Lewis structures is actually correct. And one of these is definitely better than the other. All right, so formal charge. Simple little equation. So the formal charge is equal to the number of valence electrons in the central atom. That means unbonded, before you attach anything to it, is the number of valence electrons, minus the number of lone pairs number of lone pair electrons. So it's not lone pairs, number of lone pair electrons, minus 1/2 times the number of bonded electrons. Okay, so let's take an example of what we mean by this. So for carbon, and what I'm doing is I'm gonna look at each individual type of atom that we have in it. So we're gonna look at that first, and then we're gonna look at a sulfur in this configuration. So carbon with 2 double bonds, so the formal charge is going to be equal to, there's 4 valence electrons in carbon, minus 0 lone pair electrons, minus 1/2 times 2, 4, 6, 8. So 4 minus 0 minus 4 is equal to 0, and I'm just going to put a little notation up here that the formal charge on this carbon is 0. All right? Now, sulfur with this type of configuration. It's got 2 lone pairs and a double bond. You notice that takes care of both of those sulfurs. So the formal charge on this is equal to, there's 6 valence electrons in sulfur, minus 4, 1, 2, 3, 4, minus 1/2 times 4. So this is 6 minus 4 minus 2. That one's also equal to 0. So we got a 0 here and a 0 here. All right? Now, let's analyze. So what we've done is we've just taken a look at this molecule here. Let's analyze this molecule right here. So we've got a carbon with a triple bond and a single bond. Formal charge is equal to 4 minus 0 minus 1/2 times 8 is equal to 0. So that one's a 0. And the formal charge, we've got 2 different types of sulfur now. Now we've got a sulfur We've got a sulfur with 3 lone pairs and a single bond. So the formal charge on that is 6 minus 1/2 times 2. 6 minus 1 is equal to minus 1. So this sulfur has a minus 1 formal charge. And then we've got a different type of sulfur on the other side, which is a sulfur with a triple bond and 1 lone pair. The formal charge on that is equal to 6 minus 2 minus 1/2 times 6. 6 minus 2 minus 3, that's going to equal to plus 1. So that guy has a plus 1 formal charge. All right, so how do we use formal charge to help us evaluate which of these is a better structure? Turns out this one's a better structure, and the reason why this one is a better structure is we're able to write the Lewis structure with all zeros for the formal charge. So let's make a list of rules here then for our formal charges. So the list of rules, number 1, if we can write a structure with all atoms having 0 formal charge, that's going to be the best structure. Okay, so in our example, this CS2, where all of them have 0 formal charge, that's going to be the best structure. That's rule number 1. Now, sometimes that's not possible. We'll give you an example in a second. Second will be, we want, typically, if we have to have a formal charge, we want a low number of the formal charge. So like plus 3, plus 4, minus 2, minus 3, minus 4. Those are generally not good. If you end up with a structure that has a high formal charge, it's probably not right. Low formal charge is preferred. 3, we generally want the negative formal charge on the more electronegative elements. So you want a negative formal charge on something like oxygen or on chlorine or on sulfur. You don't want it on the carbons and the hydrogens and the nitrogens. Okay, so that's rule number 3, or guide rule of thumb number 3. And number 4 is the sum of the formal charges has to equal to the charge on the molecule. So if you calculate all the formal charges, they should add up to whatever the charge is on the molecule. If they do not add up to what the charge on the molecule is, you've made a mistake somewhere. Either your Lewis structure is wrong or you've calculated the formal charge wrong. So let's take a look at what that looks like. Before, we already looked at NO3 minus. So I'll save us the hassle of rewriting the structure. We'll just write it quickly. I don't need to write all the resonance forms out for it. I'm just going to write the molecule down. All right, and with that, molecule written like that, we are now going to calculate the formal charge. So the formal charge on this type of oxygen. So it's a oxygen with 3 lone pairs and a single bond. So that would be 6 is the valence electrons, minus 6, minus 1/2 times 2. So that is going to equal to minus 1. All right, so this one has a minus 1, and this one has a minus 1. Now, we already said this is the Lewis structure. That is the correct Lewis structure, and you can see there's no way to write this without something having a formal charge. So 2 of these have a minus 1 formal charge. We have an oxygen in this form, a double bond with two lone pairs. Formal charge on this is equal to 6 minus 4 minus 1/2 times 4, and that one is equal to 0. And we've got one more type of structure we have. We have a nitrogen with a double bond and 2 single bonds. So the formal charge on this is 5 minus 0 minus 1/2 times 8. So this is equal to plus 1. Remember, I said you might have to have formal charges. All right, now, does it fit our requirements? -1, plus 1, it has to add up to the sum on the molecule. The molecule is a -1 charge. All those formal charges are going to add up to -1. That indicates to us that it's probably the correct Lewis structure. Remember, there are resonance forms for this, but that is the correct Lewis structure for a nitrate anion. And we've used formal charges to help us figure that out. All right, now, finally, let's take a look at this question right here. Which of the following is the most plausible Lewis structure for formaldehyde? You might want to take a second and pause this video and see if you can figure out which one is the correct one based on all the rules that we've talked about. Okay, we have 4 possible Lewis structures that we have identified for this molecule CHO, and a couple of them you should be able to eliminate right off the bat because of the octet rule. Well, one of them you can eliminate right off the bat because hydrogen always is in the terminal position and cannot have more than 2 bonds around. So this one is no good without doing anything else. Why? Because hydrogen, this hydrogen has 4 electrons around it. Hydrogen cannot form 4 electrons around it. So that one cannot be correct. All right, so we can eliminate B right off the bat. Now, C. What's the problem with C if you take a look at that one? If you look at C, you notice it has a violation of the octet rule for carbon. Carbon's never going to violate the octet rule. You will not find carbon violating the octet rule until middle to late organic 2. So for the next year, no molecule you're ever going to have is going to have carbon violating the octet rule. All right, so therefore C cannot be correct. So now we've got 2 left. We've got either B or A or D are possibilities. Now, if we look at the octet rules, you can see, okay, this hydrogen has 2, this hydrogen has 2, that looks good, that one has 2, that one has 2, both of those look good. This oxygen has 2, 4, 6, 8 around it, and this carbon has 2, 4, 6, 8 around it. So A could be good because of the octet rules. And then let's take a look at D. D has 2, 4, 6, 8 around the oxygen and 2, 4, 6, 8 around the carbon. So that also could be good in terms of the octet rules. So how can we evaluate? How can we tell which one's correct, A or D? Well, you know where this video is. This is in the context of formal charges. So let's take a look at the formal charges of A. Oops. So we've got a hydrogen with a single bond next to it, and the formal charge on that is going to equal to 1 minus 0 minus 1/2 times 2. That's going to be a 0. So let's put a marker. That has a formal charge of 0. That one has a formal charge of 0. In fact, every time you have a hydrogen with a single bond, it's got a formal charge of 0. Now we have a carbon with a lone pair, a single bond, and a double bond. So the formal charge on this is 4 minus 2 minus 1/2 times 6 is 4 minus 2 minus 3 is equal to minus 1. And we also have an oxygen with a single lone pair, a double bond, and a single bond. So the formal charge on this is 6 minus 2 minus 1/2 times 6 is 6 minus 2 minus 3, and that one's equal to plus 1. For D, we've got a carbon with 2 single bonds and a double bond. So the formal charge is 4 minus 0 minus 1/2 times 8. You're going to notice a trend here. Once you've done these a couple times, you'll start seeing that as a common trend. And then we also have an oxygen with 2 lone pairs and 2 double bonds. Formal charge equals to 6 minus 4 minus 1/2 times 4. That one also equals to 0. So you know where we're going with this. That's the better Lewis structure because we've got all zeros. A couple of other things to note. A negative on the carbon and a positive on the oxygen is unlikely to be true. Oxygen's the more electronegative element, so that one should have the negative formal charge on it. If there's going to be a formal charge, it should be on the more electronegative element. Another reason why this isn't good. Let me give you one more thing to just consider or to remember. As far as we're concerned in this class, carbon never has a lone pair. All right, when you get to organic 2, they're going to talk about radicals, they're going to talk about carbons having extra electrons on them, not bonded. Those are super reactive. They do not stay around very long. So you're not going to find a stable molecule with carbon having a lone pair. And carbon never violates the octet rule. At least as far as this class and Gen Chem 2 and Organic 1, carbon never violates the octet rule. Those are two ideas you should just keep in your mind. When you're writing Lewis structures, carbon should always have 4 bonds to it, and it should never have a lone pair. And then the other thing you might have noticed when we've done these different examples is every time we have carbon in some configuration, it doesn't matter whether it's written this way or this way or this way, a triple bond, a double bond, 2 double bonds, a carbon with a double bond and 2 single bonds. Any of those configurations, you notice all of those have the exact same formal charge. You can kind of save yourself some trouble because they're all going to be this, 4 minus 0 minus 1/2 times 8. So you don't have to calculate the formal charge. If you see a carbon with 4 bonds to it, no matter what the configuration is, you can just jump right to the conclusion of that one's going to have a formal charge of 0. And every one of your molecules should have carbon not with lone pairs, but should have 4 bonding things around it. All right, next video is going to talk about exceptions to the octet rule. There are not a lot of exceptions, but there are some. So you're going to learn the exceptions to the octet rule, and then you're also going to learn about bond strengths and bond lengths.